Hello, ladies and gentlemen. This is Mr. Vanskoy. We are going to start our lesson off on plate tectonics, our unit off on plate tectonics. We're going to be talking about Earth's interior today. When you're done with this lesson, you should be able to describe Earth's 4 basic interior layers from the inside to the outside. Although we're actually going to tackle these from the outside in, but make sure that you're familiar with those different layers and the correct sequence. We're going to focus on the 4 basic layers, the inner core, the outer core, the mantle, and the crust. There are actually more than those 4 layers, but these are the ones that we're going to focus on for our course. The crust includes both the continental crust and the oceanic crust. It is the thinnest layer, and often the analogy is kind of demonstrated here by my thin ring over here. And often the analogy or metaphor is used with an apple, and that the crust is like the skin on an apple. So it's important, and for us it's important because that's where we live, but compared to the thickness of the rest of the apple, that skin is quite thin. Likewise with our crust, very thin compared to the rest of the planet, but hey, it's where we live, so it's pretty important to us. The mantle is the biggest, and it contains solid but flowing rock in convection cells. And I am going to do a separate lesson talking in more detail about convection cells. But just very briefly, quickly here, convection happens when you have a fluid with a warmer fluid being heated up, or a fluid that's being heated up and then becoming less dense as it's heated up. And eventually that fluid, or in this case that rock, is going to cool down. It isn't that it's cold, but just relative to the other one, it's cooler and therefore is more dense. So the less dense, warmer rises, and the slightly cooler fluid, or in this case rock, is going to be more dense and sink down. And so what happens is we get this cycle over and over and over and over here next to it, and call those convection cells. And as I'd mentioned, the mantle is very, very thick compared to the crust and really a lot of the planet in general. So in our previous slide and in some of our other discussions, we've talked about convection cells in the mantle. But in order to have convection or convection cells, there has to be some type of heat. There has to be a heat source that's continuing this process that's driving the convection cells. So where does that heat come from? Well, it comes from the core, and it does come from deep within the Earth. But where then does that heat come from? There are kind of 2 primary sources of heat for Earth's interior. One of those is going to be a radioactive decay of isotopes. Okay? The other is going to be leftover heat from Earth's formation. They're going to supply most of the thermal energy. Okay? I have an example here of a alpha decay. With this alpha particle being given off here, 2 protons and 2 neutrons. This started off as a uranium-238, and then it's going to give off those 2 protons, 2 neutrons, and actually become a thorium-234. I am not expecting you guys to know specific radioactive decays, and we've talked about isotopes before, but I just want you to understand then that during this process, when it's changing from one particle into another, there's heat that's given off. That's why we call that a radioactive type of decay. And again, the other heat source is from really just when the Earth had formed. It was very, very hot, and because it is so big, and it's still cooling off 4.5 or 4.6 billion years later. So it's just leftover heat from its formation. Below the mantle is the outer core. The outer core is a dense liquified metal layer, okay? And it is also, because there's that liquid metal in the outer core, it's going to help generate the magnetic field, which I'll talk about next. Below that is the inner core. The inner core is a solid rotating metal sphere or metal ball. So we kind of complete my fancy diagram of science here. We've got our crust, we've got our mantle, we have our outer core, and then we have our inner core. Okay, so at the very center is this solid ball of metal. So in the outer core, it's liquid, and the outer core is the only true liquid layer that we have, made up of iron, nickel, and some other metals. In the inner core, it's going to be primarily iron. Some other things too, but mostly solid iron. And this inner core, the solid ball, is spinning inside of that liquid metal layer of the outer core. And what's going to happen there is you're going to have an electric field generated, or what we call our magnetic field. If you want to know more about that, again, it really goes beyond the scope of our introductory earth science class. But you can do some searching about dynamos or dynamo theories to go into a greater detail. Over here on the left, we've got a fancier diagram than my fancy model of science here from the USGS website, showing some of these different layers. Note that it says not to scale, but it tells us some of those different, I believe that is thicknesses, or possibly depths. No, I'm not really sure. I think it's thicknesses. So showing some of those. Earth's interior layers are mostly divided by density. So scientists, we love classifying things. So how do you classify one layer from the other? One would be to look at the different materials that make up that layer. But that is part of what affects the density. But it is really, when you get down to it, it's the density, the different densities of those layers, where we say this layer starts, this layer stops, and the other layer begins. So as we saw in some of our previous diagrams, the Earth is many thousands of kilometers thick. How do we know what's going on down inside the Earth's interior? We only have been able to drill down a few miles at most. Most of our minds don't even come close to getting through our crust. And remember, the crust is the thin part, and we haven't even made it all the way through that. So how do we know what's going on down there? We do that mostly through energy waves, and really studying energy waves. So as energy waves travel through a material, if there are different densities, it's going to behave the way those energy waves move. Or if there are different states of matter. So energy waves travel differently through a liquid than they do a solid. So by studying the behavior of those energy waves as they travel through, we can start to map out what's underneath us. In fact, this is what gas and oil companies do, is they will hire geologists to help them find what's deep down in the ground. It costs many thousands of dollars to drill wells for gas and oil. So what they do is they will hire geologists to send and set up little detonations, little shocks, that send shocks down into the ground, and then they have machines set up then to record how those energy waves are picked up by those machines in different locations. And as those energy waves, those seismic waves or shock waves, if you will, encounter different types of gases or liquids or solids, it's going to it's going to kind of leave a signature in the way that those waves both arrive and kind of the way that they travel. So they're able to use some mathematical formulas to infer what is there without actually seeing it. And the way we do this in nature, of course, is we're not sending huge bombs down into the ground to map out the Earth. It's through seismic waves from earthquakes. So there are estimated, I believe, on average about 50 earthquakes around the world every day. And so our instruments are able to measure those very small ones and measure them, those seismic waves. As you travel deeper into the Earth, the pressure and temperature increase tremendously with depth. So the further you go into the Earth, the pressure and temperature are going to increase phenomenally. So very, very high pressure and high temperatures in the Earth. I'm not going to have you guys memorize certain different temperatures and whatnot. I just want you to know the general trend. Okay, so that's going to conclude our lesson on Earth's interior. I hope that helped. If you have questions, as always, please ask.